Okay, so today we are going to talk about second law of thermodynamics. Okay, so before that we need to discuss something. Uh, First of all, we have completed the first law of thermodynamics. Now in first law of thermodynamics, what happened? We have talked about a process and a cycle and how energy is conserved in them. Okay, in a cycle what happens? The final state and initial state is same. So whatever the heat input or heat interaction is there during the cycle is equal to the work interaction during a cycle. Whereas in process what happens? In process you go from one point to another. From point 1 to point 2 there is a heat interaction and there is a work interaction. Okay, and in between this there is a change in internal energy also. That internal energy change is not considered in terms of cycle. Why? Because in terms of cycle the initial point and final point is same, and the internal energy is a property, and for a point in thermodynamics any property for a single point is always same, whether you come it after 1 hour, come to it after 1 hour or 2 hour. If you come back to the same point, the property of that system is not going to change, and internal energy is a property. So during a process you move from one point to another, so the properties like internal energy changes, whether it was from, if it was it was having some value in point 1, and in process you are changing the position. Okay, if you remember the definition of process, what we have written, we have said that it is a change of state. So during the change of state, if your state is changing, your property is also going to change. Okay, because property is something by which you define a state. So if your state is changing, property is also going to change. Okay, now these are two important points to remember for process and cycle for first law of thermodynamics. Now another thing is that in first law of thermodynamics, in every manner we have found out how work is going to get conserved in any process or a cycle. But the first law has never talked about the feasibility of the cycle or process. Okay, whether that cycle or process is going to be feasible or not. If it is going to be feasible, then what extent, up to what extent it is going to be feasible, or any matter about the feasibility, first law has not talked about it. Okay, so here the first point is, first law of thermodynamics simply says energy is conserved during a process or a cycle. It does not give any information about the feasibility. Okay, now second thing is, in second law of thermodynamics what happens? In second law of thermodynamics, it gives the criteria of feasibility of a process or a cycle. Okay, it gives the second law of thermodynamics. There are two statements for a second law of thermodynamics. If you read them, you will always see some conditions. Some conditions are given. Reading these conditions, you are going to see that if these conditions are applied, then only our cycle is going to work, or our process is going to have some meaning. Okay, second law of thermodynamics has given us the criteria of the feasibility of a cycle or a process. Okay, now it gives the direction of a particular process with the help of entropy. Okay, now again, in case of first law of thermodynamics, it did not say in what direction from 1 to, it will go from 1 to 2 or 2 to 1. We have randomly drawn some curve in PV diagram or in TS diagram, then we have randomly put some value 1 and 2 there, then we have drawn the arrow. We have assumed the direction. In first law of thermodynamics, we have assumed the direction. Either it will be mentioned, okay, either it will be mentioned in the question or in the problem that this, from this pressure and this volume, it goes to this pressure and this volume. Other than that, you cannot tell what is the direction of the process. Okay, in second law of thermodynamics, with the help of entropy. Okay, entropy is the new term we are going to introduce. We are going to introduce in our next few minutes. Okay, so second law of thermodynamics gives us the direction of the process or cycle with the help of entropy. Okay, and another thing is that all spontaneous processes in nature occurs in one direction only, that is from higher potential to lower potential. You take any spontaneous natural process, you will always see that something, the process is going on from higher potential to lower potential. If you see that water is falling from a spring, you will see that water is falling from a higher height to a lower height, or higher head to a lower head. Okay, so here higher potential is higher head and lower potential is lower head, so it is flowing in one direction. Whether you take a temperature also, it flows from higher temperature to lower temperature. Okay, higher temperature is the higher potential here, lower potential is the lower temperature, so it will always flow from higher temperature to lower temperature. Okay, now these are the 3 points we need to remember before starting the second law of thermodynamics. Okay, so the next thing we are going to read is thermal reservoir. Now reservoir is something which stores something. Okay, and water reservoir means that reservoir stores water. Okay, like that thermal reservoir is something which is going to store the heat. Okay, now these thermal reservoir are of two types. One is source and one is sink. Now this source and sink will come number of times. Okay, during the discussion of second law of thermodynamics, the source and sink term is going to come number of times, so better we know it before starting the chapter. Okay, so first thing is source and second one is sink. Now source is what? Source is a type of reservoir which can supply any amount of heat. Okay, a source is something, a source is a reservoir which can supply any amount of heat without its temperature being changed. Okay, that means there is a hot body, it is giving away heat continuously, any amount of heat. If you want to take the heat for a lifetime, you can take it. Okay, even if you are taking the heat, the temperature of that body is not going to change. Then this body is known as source. Okay, now you can see that type of reservoir which can supply any amount of heat without any change in temperature, then this is known as source. Now what can be the example of a source? The example of a source is our sun. Okay, sun can give any amount of temperature. Okay, any amount of heat. Sun can give us any amount of heat and its temperature is not going to change ever. Okay, now this is something. Now why this is happening? The sun is such a massive body. Sun is such a massive body. Whether any amount of heat it gives to Earth. Okay, if you compare Earth with sun, then the sun is a massive object. Okay, now whatever the heat is going to give, whatever the heat it is going to give to the Earth, okay, it is very negligible. Then what amount of heat the sun is storing in itself. Okay, so what is source? What is a source example? An example for source, a perfect example for source can be sun. Okay, now the second thing is sink. Sink is what? Sink is a type of reservoir which can absorb any amount of heat. Okay, in terms of source, the body was supposed to give any amount of heat. Now sink is going to absorb any amount of heat. That means there is a body and continuously heat is coming to it. Heat is coming to it, but its temperature is not going to change. Okay, then sink is something which is continuously going to absorb the heat without its temperature being changed. Then it is known as sink. Now what could be the example of a sink? The perfect example for a sink is atmosphere. Okay, atmosphere. If you continuously give heat to an atmosphere, the atmosphere is so massive that your heat input to the atmosphere is not going to change its temperature, and even if it changes, it is very negligible. It will be very negligible. Okay, so atmosphere is a perfect example for sink. Okay, so the next thing we are going to study is second law of thermodynamics for a cycle. Okay, we are going to study second law of thermodynamics for a cycle. Now there is a Joule's experiment. Okay, according to this experiment, one machine has been designed where you are going to give only heat. Okay, you are going to give only heat from a source. Okay, source means what? A thermal reservoir which can give heat continuously, of any amount of heat it can give without its temperature being changed. So from a source you are going to give heat, and that machine is going to give work continuously. Okay, if you give heat, then continuously it is going to give us work. Okay, Now, according to this experiment, what is going to be the efficiency? According to them, complete heat is going to get converted to work. Complete heat is getting converted to work. Okay. Now, according to this, efficiency is work interaction by Q input. Okay. Now, if the complete Q is going to get converted to work, that means complete Q is going to be W. Summation of Q is equals to summation of W. According to the first law of thermodynamics, then what happens? This is going to give us 100% efficiency. Okay. But we all know that what happens? Heat is a low grade energy, and work is a high grade energy. Heat is a non-organized form of energy, and work is an organized form of energy. Now, we have said earlier that we cannot convert a low grade energy to a high grade energy completely. Okay, heat is a low grade energy, so you cannot convert the total amount of heat, that is low grade energy, to work, which is higher grade energy. Okay. Now, what happens? That means what? This machine is completely impossible. Okay, you cannot convert heat to work. And another thing is that we are making sure that they are saying that complete heat is going to get transferred to work, because there is a source, but there is no sink. Okay, now whatever the heat is not been able to get converted to work should have been disposed to sink. But according to their confidence, they have said that complete heat is going to get converted to work, so they have not mentioned any sink also. So from this we can say that this type of machine is going to be completely impossible, and this type of machine is known as PMM2. Okay, perpetual motion machine 2. Perpetual motion machine 1 we have discussed earlier. Now this is perpetual motion machine 2. That means a machine which is going to get continuous work. Perpetual means continuous. Okay, so which is going to give continuous heat with by taking heat from one reservoir only. Okay, that means according to this, the perpetual motion machine is, if a machine is going to give continuous work, okay, by interacting heat with only one thermal reservoir only. Okay, now according to Joule's experiment, this is the machine. Now to oppose, this is not possible. So to oppose this kind of proposal, to oppose this kind of machines, second law of thermodynamics has been given. Okay, and this second law of thermodynamics is based on 2 or 3 statements. Okay, to oppose this type of theory, second law of thermodynamics has been given in terms of some statement. Okay, these statements we are going to read in next put. Okay, now for now we need to remember that according to Joule's experiment, whatever the machine design or whatever the proposal was given, that was not possible, and to oppose them, the second law of thermodynamics has been introduced, and this second law of thermodynamics are going to be given in terms of some statements. Okay, so the first thing we need to know that Kelvin Planck's statement. Okay, Kelvin Planck statement, this is a statement which is given on second law of thermodynamics. If you find somewhere, you cannot find a perfect definition for a second law of thermodynamics, but it is going to get clear with the help of some statements. So first statement we are going to read is Kelvin Planck statement. So according to this statement, what happens? It says that it is impossible to construct a device which develop work continuously by exchanging heat with only one reservoir. Okay, that means it is completely impossible for constructing a device. To construct a device, it is completely impossible. Okay, which can give continuous work. Okay, with exchanging heat with only one body only, or only one thermal reservoir only, it is not possible. Okay, so in last case, what you have seen, that there was only one source was given. And there was no sink. Okay, that means what? That body was completely interacting with only one thermal reservoir, that was the source, and continuous heat was continuous work was coming out. Okay, now to construct that type of machine was not possible. Okay, so this is the first statement we need to know. Now there are some other things also we need to know under this Kelvin Planck statement. Okay, so the next thing we are going to read is some heat engine or heat pump, something like that. That means we are going to give you the basic layout. We are going to give you the basic layout, okay, for which we are going to show that there are two reservoirs and how the work is coming out from heat interaction of two reservoirs, okay, two thermal reservoirs, okay. Okay, so now we are going to see the concept of heat engine. Okay, now what is heat engine? Heat engine is nothing but heat engine is a device which takes heat from a body at higher temperature and rejects the remaining heat to a body at lower temperature. Okay, now heat engine is what? Heat engine is a body which takes heat from a source of higher temperature and rejects some of the heat to a lower temperature, a thermal reservoir of lower temperature, and converts some of the heat, okay, and convert some of the heat. Suppose this according to this diagram, this is the source, and from this source Q1 is coming to a system. Okay, that red boundary we are showing this as system. Okay, now heat is coming into the system, it is coming into the system and it rejects a part of the heat, that is Q1, okay, a part of Q2, a part of that heat Q1, that is Q2, is getting rejected to a heat after converting a part of that heat to 1. Okay, that means what is happening, an amount Q1 of heat is coming from a source. After that, some of the a part of that heat is going to get converted to work. Okay, a part of that heat is going to get converted to work, and the remaining heat, after converting to work, there is some heat remaining, and that heat is going to get disposed to the sink, okay, or released to the sink, which is a thermal reservoir at lower temperature. Okay, this is the concept of a heat engine. Okay, now in heat engine, if we need to find the efficiency, okay, efficiency, what will happen? Now according to the first law of thermodynamics, this is a cycle. Okay, so the first law of thermodynamics for a cycle is what? Summation heat interaction is going to be equal to the work interaction. Okay, that means the summation of heat interaction. Summation of heat interaction. Now this is the system. Heat is coming to the system. That means it will be positive Q1, and here heat is getting rejected from a system. Okay, that means it will be minus Q2. According to sign convention, we have seen that our motto is to give heat and take out work. Okay, so we are giving heat, that means this is positive. Now here heat is coming out of the system. Heat is coming out of the system, that means this is going to be negative. Okay, now work, there is only one work, okay, which is coming out of the system. So work is coming out of the system means this is positive. Okay, now if you want to find the efficiency, now what is efficiency? Efficiency is nothing but the work output by heat input. So work output by heat input, that is the heat getting input to the heat which is an input to the system is Q1. Okay, so this will be W by Q1. Okay, now we have found out W is what? Q1 minus Q2. Okay, now we can write it here. Efficiency W equals to Q1 minus Q2 divided by Q1. Okay, so this will be 1 minus Q2 by Q1. Okay, so this is the whole concept of heat engine. Okay, so basically heat comes from a reservoir at higher temperature. Some of that heat is going to get converted to work and some gets rejected. Now from this scenario we are finding out the efficiency. Okay, now this is going to be the efficiency. Efficiency is what? Efficiency is 1 minus heat rejected by heat input. This is going to give us the efficiency. Okay, so the next thing we are going to read is Clausius statement. Okay, now it is another statement to get an idea about the second law of thermodynamics. Okay, the first one was Kelvin Planck statement, where we have said that it is impossible to construct a device which can produce continuous work without interacting heat with to reservoirs. Okay, or with interacting heat with only one reservoir, it is impossible to construct a device to which can give continuous work. Okay, that means with heat interaction with only one reservoir, it is impossible to give continuous work. Now Clausius statement is what? It is impossible to construct a device operating on a cycle. Okay, that means it is a machine is not going to be constructed which is going to operate on a cycle and transfer heat from lower temperature to higher temperature. Okay, without any external work. That means what? They have said that it is impossible to construct a device where heat is transferring from lower temperature to higher temperature without external work. Okay, now here the concept of refrigeration comes. Okay, now we need to know that we have already said that any natural process goes from higher potential to lower potential. Okay, if you take any natural spontaneous work or any natural spontaneous process, you can see that everything comes from higher potential to lower potential. Now for taking something or to reverse the direction from lower potential to higher potential, we obviously need to do some work. Like if there is a tank on the rooftop of your house, and water is coming from that rooftop to ground level easily. If you just open the tap or if you just open the nozzle, the water will automatically come from the tank in your rooftop to the ground. But if you want to take the water from ground to the tank on your rooftop, what you need to do? You need to have a pump. Okay, you need to have a pump. Okay, that means a pump is what? A pump is a work consuming device. That means by using pump we are giving heat. We are giving work. Okay, by using that pump we are giving work input, and due to this work input only, the water is going from a lower place to a higher place. Okay, so that means what? To reverse the direction from lower potential to higher potential, whether it is I have given the example of head. We are taking water from lower head to a higher head, and for that we are using one work consuming device, or we are giving heat input. Now for taking heat, we all know that heat always flows from higher temperature to lower temperature. Now to take heat from lower temperature to higher temperature, obviously we need to give some work, otherwise it is not going to happen. Okay, so they have said that it is impossible to construct a device operating on a cycle and transfers heat from lower temperature to higher temperature without external work. Without external work we cannot transfer heat from lower temperature to higher temperature. And from there the concept of refrigeration comes. In refrigeration, what happens? We take a temperature from a place, from a lower temperature, and give it to the surrounding. Inside the fridge it is lower temperature. Okay, inside the fridge it is very low temperature, and the work of that refrigerator is to take out heat from that lower temperature and give it to the atmosphere. Okay, for that we give the work input by electrical energy. Okay, we give electrical energy as work input. Okay, by this work input, what happens? Heat transfers from lower temperature to higher temperature, or from a source, from a sink to a source. Okay, from a sink to a source. Okay, that means we are reversing the direction of flow of heat from lower temperature to higher temperature. For this we need to give some external work, otherwise it is not going to happen. Okay, so the next thing is concept of refrigeration. Now what is refrigeration? Refrigeration is a refrigerator is a device which creates a temperature which is lower than the surrounding. Okay, it creates a temperature which is lower than the surrounding and it maintains that temperature. Okay, that means a refrigerator is a device which creates and maintains the temperature lower than the surrounding. Okay, lower than the surrounding. Now this is the basic layout of a refrigeration. What happens? There is a source, that is the surrounding, and this is the place where you need to maintain a temperature which is lower than the atmospheric temperature. Okay, this is the T law. this T low is lower than atmospheric temperature, and this is the atmospheric temperature. Okay, or any other surrounding you are going to consider which is higher than or any other surrounding you are going to consider. Okay, now this TL is lower than the atmospheric temperature. So from this place or from this confined region we are taking out some heat. Okay, taking out some heat, that is QL. Okay, that means the heat taken out from the lower temperature, this is QL. Okay, and this is QH. Okay, that means whatever the heat we are going to transfer to the higher temperature, this is known as QH. Okay, now as we need to maintain the temperature at T low, okay, this temperature has to be maintained here. Okay, if you cool some water, okay, if you cool some water and you put it somewhere, okay, if you suppose you have cool down a boiling water to 0 degree, okay, that means you have turned down a water which was at 100 degree centigrade and you have taken it down to 0 degree centigrade. Okay, now suppose you have put that water in a temperature of 35 degree centigrade, let us suppose. Okay, now will that 0 degree temperature water is going to be there? No, as the time passes, that temperature will the temperature of that water will try to increase and match to the atmospheric temperature. Okay, similarly, that means there was no cycle, there was only process, there was only one process. We have cooled down the water to 0 degree centigrade. Now to maintain that water to 0 degree centigrade, we need to have our process in a cycle. Okay, we need a cycle, okay, to maintain the temperature. That's why to maintain the temperature in lower temperature we need a cycle. Okay, now again to take out heat from lower temperature and give it to the higher temperature, we need some work input. This work input is W. Okay, now if we analyze the efficiency and all, that means what? According to first law, heat interaction is going to be completely equal to the work interaction. Heat interaction is going to completely the work interaction. Now this is the system. Okay, this is the system, and this is QH and this is QL. Now heat input to the system is positive. Okay, heat input to the system is positive, and heat output to the heat input and heat output or heat going out from the system is going to be QH. Okay, and this is going to be W, as there is only one work interaction, that means this is going to be W. Okay, that means QL minus QH is going you. Okay, so this is going to be minus W. Minus W, why? Because this is work input. Work input to the system is minus W. Okay, now from this equation, what you are going to get? You are going to get the QL plus W is going to be your QH. Okay, so whatever the heat or energy you are taking out from this place, and whatever the work you are going to give, that two will sum up to give, these two will sum up. Okay, these two will sum up to give QH. Okay, now in case of refrigeration there is no efficiency. Okay, there is coefficient of performance or COP. This is coefficient of performance. Coefficient of performance is what? Whatever the required heat, whatever the heat you are going to take out, okay, that means QL, whatever the heat you are going to take out divided by whatever the work input you are giving. Okay, now this is known as COP of a refrigerator. This is known as COP of a refrigerator. What is this? Whatever that heat you are taking out from the cold region divided by whatever the work input you are giving. Okay, now from here what is going to be W? W is going to be QH minus QL. Okay, from here W is going to be QH minus QL. Okay, it is going to be QH minus QL. Okay, so this is going to be your coefficient of performance for refrigeration. Okay, now what happens, the concept of refrigeration, and another thing is refrigeration effect. Refrigeration effect is what? This QL is going to be refrigeration effect. That means whatever the heat you are going to take out, from the cold region, okay, or the region where you need to maintain a temperature lower than atmospheric temperature, whatever the heat you are taking out from this thing is known as refrigeration effect. Okay, this effect, that means this heat which you are taking out from here is very important for refrigeration, concept of refrigeration. Now a very similar concept of concept like refrigeration is concept of heat pump. Okay, very similar concept is heat pump. Now heat pump is what? Heat pump is nothing but you need to maintain, a heat pump is a device which is need to maintain a temperature higher than the atmospheric temperature. Okay, higher than the atmospheric temperature. Here what happened in case of refrigeration? What happened? You need to maintain a temperature or lower temperature less than the atmospheric temperature. Now, and this thing was less than this TL was less than atmospheric temperature. Now in case of heat pump, what will happen? You need to maintain this temperature higher than the atmospheric temperature. That means this thing is going to be equal to the atmospheric temperature. Previously this was atmospheric temperature. Now this is atmospheric temperature. You need to take heat from the atmosphere and maintain a particular region higher than the atmospheric temperature. Then this thing is known as heat pump. Remaining all thing is same. Okay, all the concepts of heat pump is going to be similar. Only in case of refrigeration, this was lower than higher temperature and this was similar to atmospheric temperature. Now in case of heat pump, this is similar to atmospheric temperature, this is higher than atmospheric temperature. This thing is going to completely be same like this. Okay, now in case of refrigeration, coefficient of performance. Previously in refrigeration, what happens? This was the refrigeration effect by work input. Now this effect is going to change to QH. Okay, this effect is going to change to QH. In the refrigeration, this heat was important. Okay, this heat was important. Whatever heat we are taking out from that place to maintain that temperature lower than atmospheric temperature. Now the important thing is what is the amount of heat we are giving to the place to maintain that temperature greater than atmospheric temperature. Okay, now this heat is important. Previously this heat was important. Now the desired effect. In case of heat pump, this QH is the desired effect. We need this effect. In refrigeration, this thing was the desired effect. Okay, now this heat is going to be our desired effect. Okay, or whatever the heat we are giving to that body so that the temperature is maintained higher than atmospheric temperature. So this is the heat pump derivation. Okay, heat pump coefficient of performance, or coefficient of performance for heat pump is going to be like this. Or you can simplify this. If you divide QH in both sides, what will happen? You will get 1 minus QH by QL. Okay, QL by QH. Okay. Okay, so next thing we are going to study is Carnot cycle. Okay, so this is the diagram of a Carnot cycle. Okay, 1, 2, 3 and 4, and these processes are adiabatic processes and these processes are isothermal processes. Now why cycle is important to read the second law of thermodynamics. Okay, now if you see our basic layout diagram, whether it may be refrigeration or heat engine or heat pump, this layout is common. Okay, this layout is common. Now here what happens? Heat comes or heat goes from here. Heat comes from here, gets rejected here, or heat goes from here, gets deposited here. Okay, now within this box, whatever we have considered as system, this system is nothing but a single cycle. Okay, now sometimes that cycle is Carnot cycle, sometimes Breton cycle, sometimes a Stirling cycle, or any other cycle it may be, but this thing inside that box is a cycle. By seeing this, we are going to analyze. Next time we are going to analyze all these heat engine or heat pump or refrigeration with the help of a cycle only. We are, if you enlarge this part, it will come as this. Okay, here it is Carnot cycle. It may be different cycle also, but these cycles are the enlarged part of this box only. Okay, this cycle is the enlarged part of this box only. That's why the reading cycle for second law of thermodynamics is very important, and Carnot cycle is one of the best reference for all the cycles. Okay, it is the best reference for all the cycles. If you need to understand, if you need to analyze different cycles, then Carnot cycle is a reference. Okay, that's why Carnot cycle is very important. Now, if you know the what is the importance of cycle for reading second law of thermodynamics, this is only that part. Okay, now in Carnot cycle, what happens? In regular circulation, we get some work output and heat interaction. Okay, now in Carnot cycle, what happens? From 1 to 2, it is adiabatic compression. Okay, though this this must be something like this. Okay, so the volume from this part is getting converted up to this part. Okay, the volume is getting compressed. Okay, initially the volume was here, now it is going here. Okay, now from 1 to 2 it is adiabatic process and adiabatic compression. The first 1 to 2 is adiabatic compression, and the second part is 2 to 3. The 2 to 3 part is isothermal heat addition. Here heat is getting added. That means in the diagram, whatever heat was coming from the source, this Q in is coming from source, and 3 to 4 is going to be your 3 to 4 is adiabatic expansion. Okay, now volume is getting expanded from here to here. During the process 3 to 4 it is getting expanded from 3 to 4, and 4 to 1 it is again isothermal heat rejection process. Okay, this is isothermal heat rejection process. Now this is the basic diagram of a Carnot cycle. Okay, Carnot cycle means what? That means air will come somewhere here. Okay, if there is a Carnot engine, there would be some air input at 1. Okay, some air input at 1. Okay, and from 1 to 2 process, without any heat addition, that heat is going to get compressed, or the air, whichever. If you take any device, okay, there are many piston cylinder arrangement or something, some arrangement is there. Now at point 1, okay, at point 1 some air you have given to that system, or there is some air already present in an open system. Okay, let us take an example of a piston cylinder arrangement. Okay, piston cylinder arrangement is there. This is the piston and there is some air. Okay, now this is state 1. Okay, this is state 1. Now what happens from 1 to 2? From 1 to 2 adiabatic compression, without any heat addition, this compression is going to be there. Okay, we will compress this air. Okay, then after compressing this, the volume is going to decrease and it will going to reach at point 2. Okay, so in point 2 to 3 what will happen? Some isothermal heat addition. We will give some heat in isothermal. Okay, isothermal process is going to be there. Okay, keeping the temperature same, we are going to give some temperature. Now at 3 to 4, what is going to happen? During 3 to 4 it is adiabatic expansion. Again, without any heat rejection or heat addition, we are going to expand this. Okay, this air is going to expand. So this is going to be process 3 to 4, and during 4 to 1 what will happen? During 4 to 1 it is this thing is going to reject heat at keeping the temperature same. Okay, keeping the temperature same, this is going to give out the heat. So this complete procedure comprises of a Carnot cycle. Okay, now the TS diagram for a Carnot cycle, the TS diagram for a Carnot cycle is going to be like a square. Okay, this is the TS diagram for a Carnot cycle. Why it is square? Because these two processes are isothermal. Okay, this is isothermal. So in TS diagram, this here is T. So whichever line is parallel to this axis, whichever line is parallel to the entropy axis is going to be isothermal. Okay, so this process and this process is isothermal. So this is parallel to S axis. And after some 2 or 3 videos, whenever we are going to get entropy in entropy chapter or in this chapter itself, you can find that reversible adiabatic. Okay, Carnot cycle is completely reversible. All the processes are reversible. Okay, so you will find that reversible adiabatic process. Now there are 2 adiabatic processes. So after completion of this chapter, you are going to see that adiabatic processes are reversible, or reversible adiabatic processes are isentropic process. That means whenever there is reversible adiabatic, it is same as entropy, isentropic. That means in reversible adiabatic processes, entropy is going to be same. Entropy is same. So if entropy is same, that means what? These processes will be like these processes will be parallel to. Okay, these 2 adiabatic processes. If you number this will be 1. This will be 1, this will be 2, this will be 3, and this will be 4, similar to this one. Now process 1 to 2 is adiabatic, so this is going to be isentropic. So isentropic will be parallel to T axis. Similarly 3 to 4 is adiabatic, so 3 to 4 would be parallel to T axis. Okay, again this is isothermal. 2 to 3 is isothermal. Isothermal means parallel to S axis, and 4 to 1 is again isothermal, so this one is parallel to S axis. So in TS diagram, Carnot cycle diagram is going to be like square. Okay, so this is the basic concept of Carnot cycle. Okay, we need to know this thing because this is going to be the reference for various cycle in future cases. Okay, so the next thing we need to know is Carnot theorem. Okay, Carnot theorem states that for various cycle working between 2 temperatures, none has efficiency greater than reversible cycle efficiency. Okay, that means if there are various numbers of engines, okay, various numbers of engines or reversible engines, then none of the engine will have efficiency which is greater than our reversible cycle efficiency. Okay, so this is not possible. Okay, that means what happens? Every reversible cycle is going to give greater efficiencies than other cycles. Okay, if there are various cycles, then only the reversible cycle is going to give you the greater efficiency. Now to prove this, let us consider this system. Okay, there is a source and there is a sink. Now there is an engine 1 and this is engine 2. We are considering engine 1 as irreversible and engine 2 as reversible. Okay, now here also let us take that the conditions are same for both these cases. Okay, we are applying engine 1 and engine 2. One is reversible and one is irreversible in similar conditions. Same temperature sink, same temperature source, same temperature sink, same amount of heat is coming from this source, same amount of heat is coming from this source. Okay, Q1, Q1, Q2, Q2. Okay, now let us, to prove this wrong, let us take an efficiency. Suppose efficiency 1 is greater than efficiency 2. Okay, now we need to prove that engine 2, okay, efficiency 2 is greater than efficiency N1, we need to prove, but we are taking the reverse. And let us see that if it is going to happen or not. If it is not going to happen, that means the opposite is going to happen. First we will take the wrong assumption. This is the wrong assumption. Okay, according to this is not going to happen because engine 1 is reversible. Engine 1 is irreversible. So according to that, engine 1 should be having less efficiency. Okay, so we are taking a wrong assumption. After that we will prove this assumption wrong and we will conclude the other way around. Okay, so this is the sink, let us suppose. So let us suppose efficiency 1 is greater than 1. Okay, so what will happen? Efficiency 1 is greater than 1, that means work output from this is going to be greater than this. Since heat input is same, so work input is going to be greater than this one. Okay, Now in the next case, let us draw this again. Okay, so this is going to be our same. Okay, so this is the same temperature source with TH temperature. This is the same temperature sink with TL temperature, and here Q1 is coming and here Q2 is coming. Now this one is reversible. Engine 2 is reversible. Okay, engine 2 is reversible. So let us reverse this engine. Okay, let us reverse this engine. That means now it will take Q2 amount of heat from this sink. Okay, this and give Q1 temperature to T high. Okay, that means the source with higher temperature. Okay, now this is reversible, so we can reverse this one. So let us suppose this is engine 1 and this E is written in a reverse way. Okay, this was engine 2 and this is engine 2 in a reverse manner. Okay, so now this will take Q2 amount of heat from the same temperature sink, and this will give Q1 to the same temperature source. Okay, this is reversed. Now what happens? This is also giving Q amount of heat. This is taking Q1 amount of heat. Okay, this is giving Q1 amount of heat. This is taking Q1 amount of heat. Now here there is no need of the source now. Okay, we can directly give Q1 amount of heat to this one. Okay, now to reverse this engine, this is going to need some work output. Let us suppose this is giving W1 and here we are giving W2. Okay, so some net W is coming. Suppose W net is equals to W1 minus W2. Okay, W1 minus W2. So there is no need of this heat source now. We can directly give this amount of heat to this. We are considering this as the system. We are considering this as system. So there would be some W net here. Okay, after work output is coming out from engine 1, some part of that engine, some part of that work is going to give it to the E2. So there would be some W net. Okay, equal to W1 minus W2. Okay, this is the W net. Now if you consider this as a system, then this total thing as a system. Now what is happening from this system? We are going to get some W net. Okay, and there is heat interaction of Q2 and this Q2. Okay, now this complete system is going to get us continuous work. Okay, this thing is going to get us continuous work with heat interaction only with one reservoir only, because this reservoir has been erased. Okay, this reservoir has been erased because we are directly getting heat from this engine. This engine heat is directly getting going to this engine. Okay, so what happens? This total engine is going to work under this only one single reservoir only. Only one single reservoir. Okay, there is no need of another reservoir. So this is the violation of Kelvin-Planck statement. Okay, this is the violation of our Kelvin-Planck statement. So that is the reason, the assumption which we have taken. Okay, now this is W1, the assumption which we have taken. We are taking the assumption of W1 minus W1 is greater than W2. If W1 is greater than W2, then only we are going to get some W net. Then only we are going to get some W net. And to get W net, this system has to be there. But this system is not possible because this is only interacting with only single reservoir. Okay, this is W1 is greater than. Only if W1 is greater than, then only we are going to get W2. Okay, now to get W net, this has to be the system. Again, this system is not possible as it is the violation of Kelvin-Planck statement. That means our assumption was wrong. The reverse of it is true. That means efficiency of second engine must be efficiency of second engine is greater than efficiency of first engine, and if that first engine was irreversible. Okay, first engine was irreversible, second engine was reversible. That means what? Always the efficiency of reversible engine is going to be greater than the efficiency of irreversible engine. Okay, in the next video we are going to start with Clausius inequality statement. Okay.